Okay, so welcome back, everyone. We take it from where we left yesterday. So today we're gonna see really how a protonic description emerges from what we discussed yesterday, namely the description of a scattering process in terms of a leptonic part in DIS or semi-inclusive DIS and an hadronic part. The hadronic part, as we said, could be parameterized in terms of structure functions, which are functions that describe how the hadron responds to an excitation. And today we are going to see how to describe these response functions in terms of quarks and gluons. So today we are really going to look at the partonic content. So we're gonna look at this point here: collinear partons and non-collinear partons. Okay. Oops. Okay, I left something here. All right. So the tool that we can use, that we have at our disposal in order to study the hadronic tensor, at least in this context, in this room, is the operator product expansion that Marco Radici introduced in his lectures. So if you use the properties of the delta distribution here, the completeness on these intermediate states, Px, and translational invariance of the arguments of the currents, you can show that you can rewrite the hadronic tensor, written in this form, as the expectation value on the hadronic states of a commutator. Okay. So by the way, the delta function that was here meant that if P is the momentum of the target, the hadronic target, and Q is the momentum of the external probe, this delta tells you that the momenta had to add up. All right, so you have Q hitting the target with momentum Q. The target has momentum P, and the remnants, the leftovers of the reactions, have momentum Px. So this delta function here tells you, of course, that for momentum has to be conserved. Okay, for inclusive DIS, this is what happens at the mathematical level. You can build a commutator here of the two currents. So causality implies that this commutator here is non-zero only when psi square is larger than 0. So when you are inside the light cone, okay? So you cannot causally connect 2 points that are, let's say, at the origin and outside of the light cone. So this function here is different from 0 only if psi square, the distance between psi and 0, is larger than 0. It's space-like, time-like. The Riemann-Lebesgue lemma, moreover, implies that this function here is 0 unless psi 0 goes to 0. The technical reason was explained by Marco in his lectures. So it's due to the oscillating nature of this integral. So if you combine these two informations together, this means that this hadronic tensor here is non-zero, or it's basically dominated by what happens on the light cone. So when psi squared is equal to 0. So if psi squared is equal to 0, that means that the distance between psi and 0 is very small, of course, and this means that you can use the operator product expansion. Okay, so the operator product expansion tells you that if you have a product of operators, A evaluated at X and B evaluated at Y, you can write this product as a sum of other operators, the ON, which are regular operators, which are non-divergent, times coefficient functions, Cn, which are functions of the distance, okay? And these coefficients are, say, the ones that have some kind of divergences in them. So this is only valid when X minus Y is small, so when the distance is small. And this, applied to our hadronic tensor means that psi square has to be small. So psi square is 0 in our case, so we can use this technology here. Okay, so thanks to the light cone dominance, we can apply, as I said, this technology to the hadronic tensor. Okay, so the operators are not A and B, but are the currents in our case. And what happens is the following. So you apply the operator product expansion, and you can decompose the hadronic tensor as a sum of different contributions. And those different contributions are calculated with the OP. So the first one is a disconnected diagram. So the photon comes in and it does nothing to the hadron. The photon comes in and it excites the vacuum. It produces like any plus or minus pair, for example, and then it goes away, okay? The second one is a diagram like this one, which is called the handbag diagram, where you have a quark, the photon probes a quark, which comes out of the proton. Then the quark goes to the final state, and you have the same quark entering the hadron again. Okay, so this is really the handbag diagram that we're going to use in our calculations. And then there is another term. There are other terms. I'm only showing you the first one here, which are suppressed. These are the higher twist contributions. This is the so-called cat's ear diagrams, because it corresponds, if you can see a cat's face in this kind of diagram with the ears. Okay, if you can use some imaginations, of course. You have to use some imaginations. But this is very much suppressed in comparison to this one. So this is irrelevant. This is dominant and this is suppressed. And why is it suppressed? Because there are 4 quark insertions in the diagram. So if you think about it, it's like having a diagram which is suppressed as powers of the coupling constant, basically, but at the non-perturbative level. So the suppression is much bigger. So in a nutshell, what happens is that with the operator product expansion, we can give a partonic interpretation to our hadronic tensor. Considering the dominant contribution in the OPE, we can translate this blob here into the handbag diagram, where the photon attaches to a quark and to the anti-quark in the opposite diagram. So if you work out the calculation for this handbag diagram in inclusive DIS, what you obtain is the following. The handbag diagram can be described as a trace over Dirac indices of some gamma matrices here and a correlation function phi. Phi is a function of x and the spin of the target. So this x here is the variable that measures the collinear motion of the quark with respect to the target, the parent hadron. So what happens in inclusive DIS is that because of this diagram here, because of the structure of this diagram, you're not sensitive to transverse momentum, to the transverse momentum of the quark in the target. So that transverse momentum is integrated out, and the only dependence that you have here is on x, so the collinear momentum fraction of the quark with respect to the hadron. Okay, so what is this correlation function here? The definition is the following. It's, as we said in the first lecture yesterday, it's a bilocal operator. It's a non-local matrix elements of 2 quark fields between the hadron states with momentum p and spin s. So that function here is a function of the 4 vectors. So of the 4 momentum of the quark k, the 4 momentum of the target p, and the covariant spin vector. What we had in the handbag diagram instead was a projection of that correlation function. It was a correlation function depending only on x and the spin. All the other momentum components, k minus and the transverse momentum of the quark, are integrated out. So you will never find them in the cross-section of inclusive DIS because it's integrated out. Okay, so because of these integrations here, you evaluate this 2-point function on the light cone. So if psi plus is equal to 0, psi t is equal to 0, it means that you are on the light cone. So you have only a separation in the minus direction. So the non-locality here is only in the minus direction. This is like a cartoon, the plane where you have the minus direction and the transverse direction, which should be like a 2-dimensional space, just to show you that the non-locality in this operator is only along the minus direction. As I said yesterday, if you have questions, feel free to interrupt, to ask. We can discuss now or we can discuss later. Okay, so I told you that this object is a 2-point function, but where are the PDFs? So the PDFs come in because this is a non-perturbative object, and we know it is a Dirac matrix. As we said yesterday, what we can do is to parameterize this object here on the basis of some specific Dirac matrices. You take the base for the space of Dirac matrices. You apply some constraints like the parity invariance, the time reversal invariance of the theory, and so on and so forth. And you reduce the numbers of Dirac structures that you have available. In this specific case, for the collinear quark correlator, so for the correlator integrated over the transverse momentum, you end up with 4 different Dirac structures available. And the coefficients of this expansion are the collinear parton distribution functions. So the functions that tell you what is a probability to find a quark out of the target with a specific momentum, collinear momentum fraction. So there are 4 different terms. Okay, here I'm considering a deuteron, not just a nucleon, a deuteron, so an object with spin 1. You have the unpolarized PDF, okay, which is the simplest object. Then you have the helicity distribution, which is the PDF that tells you what's the probability of finding a longitudinally polarized quark in a longitudinally polarized hadron. Okay, so you have a dependence on the longitudinal spin here of the hadron. Then you have the transversity PDF, which tells you what's the probability to find, in a loose sense, of finding a transversely polarized quark in a transversely polarized hadron. So you see that you have the transverse spin of your hadron here. And then, since we are considering a deuteron, we have an additional term, which is proportional to one of the tensor polarization of the deuterons, okay? And so this F1LL function is the only collinear PDF that survives when you're considering the structure of the deuteron in 1 dimension. So this is the leading twist approximation. We're gonna see later what it means. But so if you relax this approximation, more functions will appear. But in the simplest case, you have the leading twist in the collinear picture. And you have 3 functions for a proton, for a spin 1/2 target, and an additional function if you are considering a deuteron. Okay, so this is the simplest picture possible. If you have questions, please interrupt. Okay, but where is the transverse momentum? So this is a set of lectures about transverse momentum, but we didn't see it yet. As I said, this is the picture for inclusive DIS, but what we need is a process that gives you an experimental handle and also a theoretical handle on the transverse momentum. On the experimental side, you will use a handle on the transverse momentum of what you measure, and your theory will connect this experimental variable to the transverse momenta of the quarks which are involved in the cross-section. So let's see how it works. This is inclusive deep inelastic scattering, where you do not measure anything apart from the lepton in the final state. If you consider another process, which is semi-inclusive deep inelastic scattering, which means inclusive DIS where you measure at least 1 hadron here in the final state, then you can also be sensitive to transverse momentum. Why is that? By the way, some terminology. So with semi-inclusive, you mean a DIS process where you measure something on top of the lepton. So you can have 1 particle inclusive DIS, which is this one, where you measure 1 particle, 1 hadron, 2 particle inclusive DIS, where you measure 2 hadrons, and so on and so forth. But generally speaking, we refer to this process as semi-inclusive DIS. So here you have the cross-section for semi-inclusive DIS. Compared to, for semi-inclusive DIS, okay, so compared to the DIS case, you see that you have a hadron that comes out of the hadronic tensor with momentum pH, and it goes through the cut. What does it mean, crossing the cut? Do you remember? It's a non-shell particle, so it's something, it's fake or it's real? It's real, so we see it in the detector, okay? So we move from DIS to semi-inclusive DIS, so you see it's more or less the same if you look at the right-hand side, but it's actually pretty different because you have a dependence on pH in the hadronic tensor. And this dependence on pH means that you can measure either the collinear part of this momentum and the transverse momentum if you want. So this reflects into the cross-section. So the cross-section is not only differential with respect to XB, like in DIS, where XB or keen was the collinear momentum fraction of the quark with respect to the momentum of the hadron, but you're also sensitive to ZH, where this Z variable measures the collinear momentum of the detected hadron compared to the axis of the fragmenting quark. And if you want, you can also measure the transverse momentum of this quark, of this outgoing hadron with respect to a certain axis. Measuring this transverse momentum here gives you the possibility to access the transverse momentum of the quark in the target and the transverse momentum of the quark that fragments, that hadronizes. Yes, okay. So compared to DIS, as we said, we have a handle on transverse parton dynamics as well. So these are the structure functions, the response functions that you can use to describe the hadronic tensor in semi-inclusive DIS. You see that compared to the DIS case, you have 3 additional structure functions. So it's a richer process because you have another vector that you can use to parameterize your gain, your cross-section. So this is the cross-section. As I said, you are differential in Z and in the transverse momentum of the detected hadron. So that means that the structure functions is also sensitive to the transverse dynamics, okay? And here is where we are gonna find the transverse momentum distributions. If you polarize the target, if you polarize the nucleon, you don't have only 5, but you have 18 structure functions. So you see that the description is much more involved compared to the DIS case. So these structure functions here depend on the polarization of the beam, so the lepton, the target, the nucleon, and also the photon. So let's consider the first one, for example. This is the simplest one. FUU, T means that it's the response function for coming from an unpolarized lepton beam, scattering on an unpolarized target, exchanging a transversely polarized photon. Okay. The same for the second, but the photon is longitudinally polarized. In the other structure functions, you don't see, in some of the other structure functions, you don't see the third index because that is irrelevant. So consider, for example, I don't know, this specific one here, which we're gonna see also later on. What do you think it is? Can you tell me? So what's the code for the subscript? Which kind of beam do we have? The beam is U, so unpolarized. The target is transversely polarized, and the exchange photon is transversely polarized. So we also have a superscript here, which is the sign of phi h minus phi s. What it means? What does it mean? It means that it's multiplied, the cross-section or the structure function is multiplied exactly by this azimuthal modulation. Okay, so it's just a convenient way to organize all the contributions. We're gonna see actually that this guy here contains one of the most interesting TMDs, which is the Sieverts function. So the idea of identifying the angular dependence is that it's just to make our life less complicated when we make an experiment. So when you make an experiment, you can also, experimentalists, please correct me if I'm wrong, but you can make a Fourier analysis of your signal, and you can actually single out all these contributions here because they have a different angular dependence. So knowing that, if you know that the Sieverts function goes together with this sign phi h minus phi s dependence, it's actually good to make a Fourier analysis of your signal and single out exactly that contribution. So this is the description for the polarized nucleon, okay, spin 1 alpha. We don't know what happens for spin 1 yet. So I put a question mark here because this calculation for spin 1 is not complete yet in the literature. There are several papers that address, for example, models for the quark TMDs and the gluon TMDs in a deuteron, in a spin 1 case, in a spin 1 hadron, but we don't have the cross-section for semi-inclusive DIS with such a target yet. So one nice project, for example, could be to sit down and calculate this kind of decomposition in structure functions for the deuteron case, including also the higher twist contributions. Okay, so this is something that I believe it's interesting to look at. Okay, so let's get to the TMDs. This is our hadronic tensor for the semi-inclusive DIS case. We just know about this blob right now. The ideal case would be to be able to apply the operator product expansion again in order to obtain something like a handbag diagram here. Unfortunately, the operator product expansion is not applicable to this hadronic tensor because of the produced hadron, because here you have px in the ket and px in the bra. So those states there, they prevent you from using a completeness relation, and they don't allow you to construct a commutator. So you cannot really have a light condominance applied to a commutator. Are we lost? No, luckily. As Marco explained in the first lecture, one can try to use an approach which basically relies on the result of the operator product expansion, and it applies it to other processes as well. This approach is called the diagrammatic approach, and it basically boils down to using a combination of handbag diagrams. So here you have a handbag diagram for the target and something like a handbag diagram for the production part to build the cross-section. Okay, so this is not formally exact, but the nice thing is that it corresponds to the results that you can get formally in TMD factorization when there is a TMD factorization theorem for such an observable. So for example, for semi-inclusive DIS, I cannot apply the OPE, but I decide that I want to use the diagrammatic approach, and I build the hadronic tensor in this way. Now, suppose that I want to study this process from the point of view of John Collins' book, which is based, which does not use the diagrammatic approach and the operator product expansion, but uses the Libby-Sterman analysis to identify the singularity regions in the diagrams which are involved in the process. I use that approach. I do all the calculations. I take into account the UV and the rapidity divergences of my diagrams. I work out the cross-section, and I obtain a result which is identical to this one, but with the objects properly renormalized. So the diagram, this is to tell you that the diagrammatic approach is not formally exact like TMD factorization or the operator product expansion in DIS, but it gives you reliable results. When you don't have, when you apply the diagrammatic approach to a process for which TMD factorization from the point of view of perturbation theory does not hold, that's a problem, okay? But you have the TMD factorization side that tells you that what you are doing is not formally exact. Is it meaningless? I don't think so, because by using the diagrammatic approach, you can build a cross-section as a function of TMD objects, even when TMD factorization is not formally applicable. And you can use the comparison between these two results to study possible TMD factorization breaking effects. So you can study in which regions, in which kinematics, the factorization assumptions are broken. This is, say, a more difficult topic. I'm not gonna touch upon it in the lectures, but if you're interested, we can talk about it later. Okay, so back to the hadronic tensor. So if you describe the hadronic tensor with this diagrammatic approach, where you reabsorb also the soft parts inside of the phi and the delta correlation functions, you see that you can write it as a convolution of these correlation functions phi for the target and correlation function delta for the hadronization part, where the convolution C is defined in this way, okay? So the important part here, what I want you to focus on is the following. The convolution contains an object F, which is one of the TMD parton distribution functions for the target. And this function here depends on the transverse momentum of the quark inside of the target. And the D is one of the fragmentation functions. So those functions that tell you what's the probability that the quarks with momentum K fragments into a specific hadron, like a pion with momentum pH. And that function is a function of the transverse momentum of the quark going into the final state. The important thing, the even more important thing to notice is the role of the delta function. The delta function tells you that if you combine PT, the transverse momentum of the quark in the target, and KT, the transverse momentum of the quark which is hadronizing, you reconstruct pH perp, which is what you measure. So you get a number from the experiment for this variable, okay? So this formula here actually allows you to connect what you measure in the transverse momentum with the transverse momentum physics in the target and in the hadronization part. Okay, so this is very important. Is it clear? Are we on the same page? If you have questions, we can stop 1 minute and think about it. Okay. So if the formalism did not allow me to connect the transverse momentum in the hadron, in the target, and in the hadronizing part with what I measure, the formalism would be useless. Okay. So, but this is very nice, I believe. Okay. So let's now look at the TMD case for the correlation function for the target. So what happens is the following. Now I integrate my form momentum. I don't integrate my form momentum on the transverse momentum anymore. So the correlation function here depends on PT as well. And you see, the 2-point function is evaluated only xi plus equal to 0. So we are not on the light cone anymore. But the separation in the transverse plane and the minus direction is the following. Okay, so you have xi minus and xi-t separation. This is going to be very important for when we consider the role of Wilson lines. Okay. Okay, so this is the table that tells you how we can organize the TMD parton distribution functions according to the nucleon and the quark polarization. So a few slides ago, let me go back. I showed you that in the collinear case, we can, in the collinear case, we can organize the correlation function with 4 different, let's consider only the nucleon, with 3 different Dirac structures whose coefficients are the collinear PDFs. In the TMD case, we can do a similar thing, but we have another vector that we can use to build these kind of structures. We have the transverse momentum of the quark. So the Dirac structures that you have are not 3, but are 8, and you're going to have 8 different coefficients, which are the 8 TMD parton distribution functions at leading twist. Okay. And those 8 coefficients are organized in this table here. Okay. So let's see for a second what they mean. So the rows correspond to the quark polarization. So the rows correspond to the nucleon polarization and the columns to the quark polarization. So F1 is the TMD PDF for an unpolarized quark in an unpolarized nucleon. F1T perp here is the Sievers function. So it's the TMD PDF for an unpolarized quark in a transversely polarized nucleon. So let's look at the color code, and the same thing holds for the other ones. The color code means that the black ones and that are on the diagonal are the 3 functions, the 3 coefficients that survive also at the collinear level, in collinear factorization. All the other ones, all the other 5 ones do not appear in the collinear case because when you integrate over transverse momentum, they disappear. The mechanism is slightly different distribution by distribution, but the bottom line is that they don't survive at the collinear level. The blue ones are the so-called TMD time reversal even, and the red ones are the time reversal odd ones. So these functions here have specific properties under the time reversal symmetry, and we're gonna see what it means later on. But the most important thing to keep in mind is that they become process dependent. So let's stop for a second. Would you be okay with a parton distribution function that depends on the process? Who would be okay with this idea? Having a PDF that depends on the process. No one is okay with it. So I assume everyone is not okay. Why are you not okay with an idea, with this idea? The PDF depends on the process. Take the microphone.
PDFs, we have this collinear Wilson line contribution is negligible. So the Wilson line gives the contribution for this process dependence.
No, but okay, yeah, but so what's the problem with the idea of having a PDF which is process dependent? Indeed, and there is even, so this is the practical problem, but there is a conceptual problem also. So the conceptual problem is that you lose the idea of hadron structure, right? So it doesn't make any sense that the structure of a hadron changes according to the way you probe it. So if we say that the PDFs are universal, it means that they cannot be process dependent, okay? But I can assure you that there is a way out, okay? So are you curious? If you are curious, I can tell you immediately, otherwise we can wait a few slides. Okay, you can wait a few slides, all right. All right, so this is the more complicated table. So this one with the 8 distribution was for the nucleon case, spin 1/2. If you consider a deuteron, you don't have 8 functions only, but you have other functions here. You get to 18, so you add other 10 TMDs related to the tensor polarization of the deuteron or the spin 1 particle that you are considering. I know that some of you have worked on calculation of these distributions for a row, okay, which is a spin 1 particle, but it's difficult to use a row as a target, right, in a scattering process. So it would be ideal to get information for the deuteron, for example. Yeah, all right. So the color code is the same. So all the red ones are T-odd. Okay, so let me say a couple of words also about the fragmentation correlator. So the fragmentation correlator is the object similar to the PDF correlator that defines the fragmentation functions. So you see, you have a quark, okay, that fragments into a specific hadron with momentum for momentum pH and spin SH. And of course, the quark does not produce only a pion, it does also many other things, produces many other hadrons. But those hadrons are neglected and they are summarized by this blob here, okay? So also in the TMD case, the non-locality is the following. So you have a displacement which is not only along the plus direction, but it has also a transverse component. The difference with respect to the PDF case is that you start from a vacuum state, okay? You don't start from an hadronic state with momentum P, and you produce hadron with momentum pH with spin SH and X, which are all the other quantum numbers that you're not observing. Okay. You have a similar table for the fragmentation functions compared to the PDF case. At leading twist for a spin 1/2 hadron, so if you're producing a spin 1/2 particle, you have 8 TMD fragmentation functions. But since measuring polarization in the final state is kind of difficult, usually people only care about the first row. So the unpolarized nucleon production, unpolarized hadron production. The first one is the TMD fragmentation function for an unpolarized quark fragmenting to an unpolarized nucleon, unpolarized hadron, and this one is the so-called Collins function. Tells you the probability that a transversely polarized quark produces an unpolarized hadron. Okay. Yeah. Okay. So something that I recently worked on is the connection to the fragmentation correlator or the fragmentation functions to the properties of quark propagation. So maybe I already spoiled it, but let's try to think about the picture of a quark which is hadronizing and producing. It's first fragmenting, so there is a shower of quarks and gluons, and then it hadronizes at a certain point. So these quarks and gluons, they recombine and they produce, I don't know, 127 pions. So the fact that you have a cut here, it means that there is hadronization at a certain point. So this shower of quarks and gluons becomes a real thing. So you have hadrons that go to the final state. Quark propagation works more or less in a similar way. Okay, so if you imagine a quark which is propagating from point X to point Y, the quark, in a sense, fragments, excites quarks and gluons from the vacuum, but it can also have hadronic contributions in the virtual states that it produces. The connection between the fragmentation functions and the correlator comes in thanks to a sum over the produced hadrons and an integration over the hadronic momenta. So if you take the correlation function for the hadronization mechanism, you perform this kind of sum, you get the quark propagator with a discontinuity. Okay, this is very interesting because it allows one to connect the hadronization mechanism to the properties of the quark propagator. You can connect the fragmentation functions, for example, to the spectral functions that you can use to describe the quark propagator. This is like totally another topic that would deserve another lecture. But why I want you to remember is that you can link some of the fragmentation functions in here with specific properties of the propagator. So for example, there are certain fragmentation functions that appear at twist free, which are related to the dynamical generation of mass in the propagator. So fragmentation functions are very interesting, also because you can define these kind of relations to the most important properties in QCD. Okay, so you can link hadronization and chiral symmetry breaking, for example. Okay, so I'm almost done. Don't worry. I just wanted to show you what happens in the case of gluons, because life is not only made out of quarks. You can have distribution functions and fragmentation functions also for gluons. The operators are just slightly different. You can have, for example, in the PDF case, in this hadron structure case, the operator is not made out of psi bar psi, but you have this combination of the field strength tensors to extract a gluon with momentum p from your target, or to describe a gluon that's fragmenting with momentum k into a specific hadron with momentum p. All right, so this is a table that compares the collection of the quark TMD PDFs and the gluon TMD PDFs. So instead of the polarization of the quark here, I brought the Dirac structures and the Lorentz structures that define these structures here. Of course, you see that for the gluon case, we are not working in a Dirac space, okay, but we have Lorentz indices. So the structures that you can use to define them are Lorentz matrices. So we have 8 TMD PDFs for the gluons as well. These 8 TMD PDFs are a little bit more tricky to study from the phenomenology point of view, because it's more difficult to construct from the point of view of TMD factorization observables which are directly sensitive to these. The phenomenology is a little bit more rich for the quark case, and also we have more data, experimental data for the quark-induced processes. This is what happens also if you consider a deuteron, so the table becomes more rich. Okay, so I think we are almost ready to tackle what is transverse momentum imaging. So to really try to understand how to start from experimental data, to start the process that leads us from experimental data for cross-sections and asymmetries to information on TMD PDFs and TMD fragmentation functions. Tomorrow we're going to see, for example, what happens when we get data for semi-inclusive DIS from Hermes, Compass, or the future EIC, or data from Drell-Yan from the existing facilities in order to understand how to get information on the TMDs. Okay. Okay, I put this here, but I'm going to discuss it tomorrow. So these are some of the processes that are sensitive to gluon TMDs. You have to look at things like scattering of an electron of a proton, where you produce 2 jets in the final state, or a J psi and a photon, or a pseudoscalar state like an eta C or a Higgs boson. But okay, this is also going to be discussed next week, I think, because some of the experts working on these processes are going to be here next week. Okay, so in the last few minutes, let's summarize what we understood so far for DIS and semi-inclusive DIS. And then we're going to say a couple of words about higher twist. For inclusive DIS, I hope I convinced you that we can do only collinear imaging. So the structure functions that you can use to describe your hadronic tensor and the cross sections, they can be turned into combinations of collinear parton distribution functions. Okay, so you have the unpolarized PDF here, the helicity PDF, the transversity PDFs, but these are only collinear distributions. If you want to do, okay, and so and these are examples. This GT here is an example of a higher twist distribution, which is suppressed by a factor m over q. If you want to measure transverse momentum, you have to go to semi-inclusive DIS and measure the transverse momentum of the hadron in the final state. For example, you have, in this case, the unpolarized structure function, which is a convolution of the unpolarized TMD PDF and the unpolarized TMD fragmentation function, where the convolution is defined in this way that we discussed previously. So you have the delta function that connects the measured transverse momentum with the transverse momentum in the target and in the fragmentation part. The other structure functions, you know, there are 18 of them, I didn't write them all here, are related to the polarized distributions. For example, this one here, which is a specific azimuthal modulation of the unpolarized cross-section, is related to the Bohr-Mulder's function, H1 perp, and the Collins function, capital H perp. So these are examples of transverse momentum odd, time reversal odd distributions. Another one, which is easier to address also from the experimental point of view, is this one, which is proportional to the convolution between the Siever's TMD PDF and the unpolarized fragmentation function. So you can access this one, as we said before, when you have an unpolarized lepton beam and a transversely polarized target. Okay? So you need polarization in the transverse plane in order to access the Siever's function. Okay, so this is the picture at tree level, of course. I didn't mention it, but if you work out this kind of calculation in perturbative QCD, on top of these convolutions, you have some hard coefficients here that give you the structure in perturbation theory as well. So as we said, so these structure functions here are related to the Siever's effect, the Collins effect, and if you want to do more complicated stuff, you go to higher twist. The higher twist structure functions are observables which are suppressed by inverse power of Q, and Q is the hard scale of the process. Okay, so the hard scale of the process in this case means that you're considering the invariant mass of the exchanged photon. So m is the mass of the target. So let's consider if we do something like, I don't know, semi-inclusive DIS at the compass experiment, m is 1 and q is 10, more or less. Yeah, that's maybe a bit an overestimate, but that tells you already that these signals here are suppressed with a factor of 10 with respect to the other ones, So the higher twist signals are, first of all, suppressed, and as you see, they are more involved compared to the other ones because they are combinations of different TMD PDFs. So you have, for example, this signal here, which is proportional to E, that we didn't see in the previous slides, but it's one of the twist-free PDFs. But you not only have this one, you have 1, 2, 3 more signals. So you combine 4 different signals in the same structure function, and everything is suppressed. So in order to get information, experimental information on this, in order to get phenomenological information on this E function, you have to get experimental information on this modulation of the cross-section. But then you have to try to disentangle this one from the other 3, which is a mess. This is why the phenomenology of higher twists is not that, let's say, it's not that established as the one at leading twist. Okay, at leading twist, the signals are not suppressed and they are cleaner because they are only proportional to some specific convolutions. Okay, let's try to say a few more words on higher twist. So looking at Marco's slides on the first day, you can see that some specific observables like cross sections or asymmetries in QCD, they can be decomposed into different ways, which are complementary, actually. So you can work out a perturbative expansion for the observable, so you can calculate the radiative corrections to your cross-section, where you have powers of the coupling constant. But you can also introduce these kind of corrections, powers of m over q, where m is the target, the hadronic target, and q is the hard scale of the process, like the invariant mass of the photon in semi-inclusive DIS. And these corrections here are called power corrections or higher twist corrections, okay? So you can try to work out, for example, TMD factorization at leading twist for an observable, which means that you stop at this level, at 1 in the power correction, and you factorize the cross-section at all orders in alpha strong. What people recently started doing is the same thing at twist 3. So they take the cross-section for semi-inclusive DIS, and they try to give it a TMD interpretation at m over q order. This is much more complicated compared to the twist 2 case. Okay? So these two expansions are complementary, and in principle, you can go in one direction or the other. This direction is much more complicated than the other, but I argue that it's also much more rich from the physics point of view, and I'm gonna tell you why. So this is what happens to your PDFs, collinear PDFs, if you add the twist 3 level. So at the twist 2 case, you only had 1, 2, 3 PDFs for a nucleon, for a spin 1 half particle. If you take into account higher twists, for example, twist 3, you have 1, 2, 3, 4, 5, 6 additional PDFs. So the table, the picture is already much more complicated. Formally, you can go even higher. You can even have twist 4, but at this point, I think up to now, I didn't see anyone really worrying about these kind of corrections in an observable. You can, of course, calculate in models these distributions to see if they respect specific sum rules or their behavior, but no one ever took into account this correction in an observable, as far as I know. Okay, so the same thing happens for the TMDs. You have 8 TMDs at twist 2, at the leading twist. These are the ones that were in the table that we saw before. If you turn on the twist 3 corrections, you get these other contributions here, which are also as complicated as the previous one. Okay, so this is, as I said, you can derive this kind of corrections in the diagrammatic approach, but the interesting thing is that you can now, some groups started giving interpretation of higher twist effects in TMD factorization as well. And what is nice to see is that the two descriptions match. Okay, so this is very interesting. So even if you do the same kind of calculations using perturbative QCD and the normalization group equations in the proper way, the expansions that you get are the same, or they can be connected to each other. Okay, so this is what happens to the C-disk cross-section if you work at twist 3. So the hadronic tensor that we considered before was only the first part here. So you had the delta function, okay, connecting the measured transverse momentum and the transverse momentum in the target in the hadronization part. And we only had the trace of the phi and delta correlators, which is this diagram here in the top left corner. So this is the twist 2 contribution. If you turn on the twist 3 correction by adding gluons coming from the target blob or the hadronization blob, you get the higher twist corrections. So how do you describe these kind of things? So these correlation functions that in the literature you can find with the name phi with a subscript capital A are free parton correlation functions. So are objects which are of this form. Okay, so you have, in a nutshell, you have the insertion of another gluon in the matrix element, okay, in another space-time point. So you have psi bar and psi in the leading twist case. At twist 3, you include a gluon, okay? So the gluon which is attached to the blob corresponds to this field here. And you can do the same for the hadronization part. So you can have free parton correlations also in the hadronization part. So you have something like this. You have a psi bar and A, and then you have the intermediate states with the measured hadron. And So compared to the twist 2 case, you have the insertion of a gluon. Okay. So the description of these matrix elements in terms of parton distribution functions or fragmentation functions is more complicated because you have another field, basically. And with this other field, you can have richer Dirac structures or Lorentz structures if you're considering gluons. Okay, so I invite you to check this paper out, which tells you how to build the cross-section of CDs considering these corrections here. Yes?
Yeah, so regarding these gluons in twist 3, so would you like to comment on, I mean, going beyond the Wenzhura-Wilczek approximation? I mean, the tilde term for the higher twist. So,
which approximation?
WW approximation in the higher twist. Wenzhura-Wilczek.
It's gonna be in the next slide.
Ah, okay.
Okay. Okay. Thank you for the question. It's very important. Okay. So at this point, let's keep in mind that we have in the red boxes we have correlation functions that depends on 3 fields. Okay. So luckily one is not lost among in this zoo of distribution functions at twist 2 and twist 3 because you can connect them to each other with what are called the equations of motions. Equations of motions are nothing else that applying the Dirac equation to these matrix elements and derive a connection with the twist 2 operators. So this reference here tells you exactly what I mean, not exactly, tells you what I told you now in a better way, okay? So the equations of motion allow you to connect twist-free fragmentation function like the scalar PDF, the E, with the functions, the same function, the same scalar PDF with a tilde, and the tilde means that it's a function that comes from this operator with an extra gluon here. So it's a quark-gluon-quark correlation on what is called a dynamical higher twist or a dynamical 3-parton correlation with a twist 2 function, F1, which is the simplest one, the unpolarized, suppressed by a mass factor. So why I'm saying it's suppressed? Because here you have the current quark mass, which is miserably small, divided by 1 GeV, if you're considering a nucleon. So this one, say, is a suppression factor that is supposed to make F1 on the same, more or less on the same level as the E tilde fragmentation function. So you see that, in a sense, the equations of motions, they tell you that the free parton fragmentation, parton distribution functions, so the dynamical higher twist, should be, you can think about them as the twist 2 reduced by these kinematical factors. So this is a quark-gluon-quark correlation in this sense. They come from this kind of operators. And then you have the twist 2 function times a mass ratio. So you can build another equations of motion for the corresponding fragmentation function. So there are lots of these equations of motion. So I'm just pointing out these 2 because I think they are useful for what I want to say. And for a specific fragmentation function at twist 3, you have this decomposition in a term which is quark-gluon-quark, so coming from this operator here, and the unpolarized fragmentation function reduced by this ratio here. What happens at this point? If you apply the sum rules for the fragmentation functions, you notice something very interesting. Starting from this equation here, you can get a relation that involves the integral of this fragmentation function. So if you integrate over Z, let's look at this one first. If you integrate over Z, the unpolarized fragmentation function, and you multiply by the mass, you get 1. So this term here actually gives you, integrated and multiplied by mh, gives you mq, which is the current quark mass. The other 2 fragmentation functions, they tell you that you can decompose the mass of addressed quark, so the physical mass of a quark, as the mass, the current quark mass, the mass that comes from the Lagrangian, from the Higgs mechanism, with a mass which is generated by an integral of these quark-gluon-quark correlations. So the fragmentation functions and the equations of motions, they give you a way to decompose the contributions in the quark mass. So they give a way to represent the quark's mass by a term which is generated by the explicit breaking of the chiral symmetry and the term which is generated by the dynamical breaking of the chiral symmetry. So it's a mass which is generated by this kind of correlations between quark, gluon, and quarks. Okay. So this is exactly what I said now. So going back to your question, if you want to make your life easier in the field of twist-free physics, you can work with the so-called Vanzura-Wilczek approximation. For the friends, is the WW approximation. Okay, that stands for Vanzura and Wilczek. This approximation corresponds to killing all the terms that are dynamical. So since describing this kind of free parton correlation functions is highly non-trivial, people say, okay, let's consider higher twist physics without these dynamical terms. Let's consider only the twist-2 terms suppressed by these mass ratios. This is legitimate. I mean, it's, you can do it if you want. But what I want to argue here is that it's very dangerous. Because if you do this approximation here and you propagate the information to the last equation, you see that you're killing really the term that generates the physical mass for the quark. Okay? In this term, in this equation, you're actually saying that the mass of a physical quark is just the Higgs mass, which is of course wrong. And you can have a similar equation for the generation of transverse momentum that I don't have time to discuss now. Okay. So I think this is my last slide. This lecture was a bit dense, I believe. So the take-home messages, I think, are the followings. If you want to measure transverse momentum physics, you have to go to a process that gives you an experimental handle on transverse momentum, like semi-inclusive DIS or Drellian or other processes that we don't discuss now. This kind of transverse momentum physics can be addressed with certain approximations. If you neglect power corrections or higher twist, you have 8 distribution functions depending on transverse momentum and 8 distribution functions that in the hadronization sector. If you turn on higher twist correction, the picture becomes much more involved. You can simplify this picture by neglecting the dynamical contributions, but what I want you to remember is that it's a very, very, very crude approximation because you are neglecting all the interesting physics. Okay, thank you.
After the coffee break, meanwhile, any urgent question? Yes.
Hello. Yeah. So you mentioned the chiral symmetry breaking is related to the hadronization.
Yes.
Can you elaborate a little bit about that?
Yes. So okay. So the idea is the following. The idea is that the idea is that you can connect the hadronization correlator to the quark propagator by means of some rules. So integrating over the hadronic, the moment of the produced hadrons and summing over these flavors of the hadrons and their spin. If you do that, you really are left with the operator that defines the propagator with a cut, so with the discontinuity of this propagator, okay? If you elaborate more on this equation, you realize that you can relate some of the fragmentation functions that are here to the spectral functions that describe the physics of the propagator. So one of the spectral functions here is the spectral function whose integral is related to the E fragmentation function that was in the last equation I had. Almost there. Okay. So this capital mass here is the mass term in the propagator, which is related to what in the propagator, in the language of the in the language of the gap equation for the propagator is the mass function. Okay, so this capital M here is related to the integral of the mass function, the discontinuity of the integral of the mass function. But so that means that this mass function here, the rest mass here, contains mainly the physics coming from the gluons. So the dynamical mass of the quark. And that dynamical mass is generated by the dynamical breaking of the chiral symmetry. So the breaking of the chiral symmetry that happens not explicitly because you put this mass here in the Lagrangian, but the breaking that happens because the quark propagator acquires a dynamical mass. So it's a connection that emerges only at the twist free level. You don't really see the connection between hadronization and this dynamical chiral symmetry breaking at twist 2. You have to go to these kind of observables, which are more difficult to study. But you can work out relations like this one, where you have the mass of the quark in the propagator language related to the mass generated by the Higgs mechanism and something which is generated by these operators.
Because the dynamical generation of the mass, which is related to chiral symmetry breaking, is a non-perturbative effect.
Exactly, exactly.
So that is coming from the...
it comes from those non-perturbative matrix elements.
Yeah. Okay. So it is a perturbative calculation, but it is coming from that, the twist calculation.
So what did you say? It's not a perturbative calculation. It's a non-perturbative statement.
The twist expansions.
Which expansion?
The twist.
The twist expansion. Yeah, the twist expansion comes from the OPE. Okay. Then, I mean, the formalism of the chiral symmetry breaking is, I mean, as far as I know, is described in another language. I mean, when I worked out this kind of relation, I was trying to interface, I mean, the language, for example, coming from the Dyson-Schwinger equation, the gap equation for the propagator with this branch of hadronic physics. So there is a lot of work to do on these kind of relations. Try to renormalize these quantities, try to understand what happens if you include other kind of corrections. So it's here, I mean, it's not, I would say it's not very well established, but we know that there is this kind of connection. So if you want, I would say it's an active field of research.
While discussing about the high twist TMD, can you comment on the charge associated with this TMD, like global charges?
Yeah, okay. So you mean, okay, like the integral of this small e PDF. Yeah, so that's the so-called scalar charge of the nucleon, which is related to the quark content. So the part of the hadron mass, which is generated by quarks. So you have three kinds of relations. For example, for the F1, you have the vector charge. The integral of F1 is related to the vector charge, which is related to the number of quarks, valence quarks that you have in the nucleon. For the transversity PDF, you have the tensor charge. And for the E PDF, you have this kind of scalar charge, which is related to the quark content of the nucleon mass. Anyone correct me if I'm wrong. No, it's not the form factor, it's the number. When you integrate E, the charge of the scalar form factor, okay. But isn't it related to the quark content of the nucleon mass? Not the dynamical one, the sigma term. I think it's off.
Which is related, yes, is related to the quark contribution to the mass of the nucleon. And also, can I make a remark
Of
about
course.
this one? Normally, when we say always that the mass of the quark contribute 1% to the mass of the nucleon, because we just take the current quark mass and we sum the mass of the current quark, and then it's about 1%. But in reality, the quark contribution to the mass of the nucleon is just related to the sigma term, which is about 10%. So then now it's popular to say it's 1%, but in reality, what is related to the quark of the mass, which is the X contribution, is about 10%. It comes from the term which goes like m psi bar psi. From this m psi bar psi is about 10% when you calculate. It's not just the sum of MQ, which would be 1%.
Thanks to Andrea for a very nice presentation.